Okay, what I'm going to do with this vodcast is go through the answers and explanations for your homework from page 828 through 831. So have your homework with you and check the answers as you go. And again, don't be afraid to pause and rewind. And then write down any questions that you have that we can address later in class. Alright, let me get myself a pen here. Alright, so the first question, and you should have your book handy so you can read the actual question. I have the question summarized, but if you have the whole question in front of you, that would be a little bit better. So anyway, number 18 says, which of the following processes are spontaneous? So again, a spontaneous process is a process that happens without outside influence. So clearly a house being built is going to be a non-spontaneous process. In other words, you've got to put work into building the house. A satellite being launched is also non-spontaneous. That doesn't happen without outside influence. A satellite falling back down to Earth is a spontaneous process. That is what wants to happen. So without outside influence, that satellite will eventually be overcome by gravity and fall back to Earth. And a kitchen getting cluttered is also spontaneous. And again, this seems to be the one that people had the most question about. But remember, if you are specifically trying to clutter the kitchen, then you are actually putting something in a certain place, so that would be a spontaneous process. But cleaning up the kitchen is going to be the non-spontaneous. Things getting cluttered around the kitchen will be a spontaneous process. So again, the whole idea of this question is to look at entropy and what processes are increasing entropy or decreasing entropy. Okay, let's take a look at the next slide. For number 20, the question says, in rolling 2 dice, what total number is the most likely to occur? Well, that number is going to be 7. And the reason for that is because there are more combinations of numbers for 7. In other words, if you're unsure, write the numbers on the dice, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6 representing the other dice. So the options to add up to 7 are going to be the most. You've got 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, etc. Numbers such as 2, the only option is going to be a 1 and a 1. So there's only one option to roll a 2. Is this an energy reason? And no, it's not an energy reason. It's simply a probability reason. The point of this question is to get you thinking about probability versus spontaneous processes with entropy increasing. Next part says, would energy be needed to increase the probability of another number? And you would have to put energy into cheating to get another number. So if you're putting energy into something, again, that's going to require an effort and require work. Okay, let's take a look at number 22. Number 22, the question reads, choose the substance with the greater positional entropy in each case. So what you're looking at is you're comparing one system to another system and deciding which has the greater entropy or positional entropy. Remember, entropy is a measure of disorder. So we have 1 mole of helium and 1 mole of helium at the same temperature, so the only difference is 1 atmosphere and 2 atmospheres. So to maintain the same temperature, if you are increasing the pressure, that means you're going to be decreasing the volume. So a smaller pressure on the system will have a greater volume, so you're going to have more opportunities for different positions in the molecules versus a smaller volume, smaller positions. So less pressure is going to mean greater positional entropy. If you look at the next one, You've got 1 mole of helium at STP. Remember, standard temperature for thermodynamics is going to be 298 kelvins, and at 1 atmosphere. So you're decreasing the temperature, but you are increasing that pressure to 2 atmospheres. So again, if you have a smaller pressure and greater temperature, you're going to have a greater positional entropy at those conditions. So again, you've got a greater temperature, which is going to make those molecules try to move apart further and faster, but you've got less pressure, so greater volume. If you've got 1 mole of helium solid at 0 K and anything at any temperature, 0 kelvins means 0 entropy, so clearly you're going to have more positional entropy with that scenario. Okay, let's take a look at number 25. And number 25 reads, predict the sign for delta S of the surroundings. So again, you want to pay attention to delta S of the surroundings. So when you're looking at the system here going from liquid to gas, you're increasing the entropy because you're taking something from a more ordered state to a less ordered state. So you're increasing delta S of the system, which means you have to decrease delta S of the surroundings. If you take a look at the next one, you're going from gas to solid, so you are decreasing the entropy of the system, so you are increasing the entropy of the surroundings. Another way to look at this problem is look at the fact that through whether or not it's exothermic and endothermic. If you're boiling liquid, in other words going from liquid to gas, that is going to be an endothermic process. So you're taking energy into the system, so you're taking energy out of the surroundings, which is going to also be a decrease in entropy. And if you're going from gas to solid, in other words you're cooling this down, that's going to be an exothermic process, so heat is being released into the surroundings, so your delta S value for the surroundings will also increase. So you can look at that from system and surroundings idea or an exothermic and endothermic idea. Okay, let's take a look at number 26. Number 26 reads, calculate delta S of the surroundings for the following reactions. So if you're calculating delta S of the surroundings, we can use our equation. Delta S of the surroundings is equal to negative delta H over our Kelvin temperature. So I'm not going to write the reactions here, and you're given your delta H values, and you're told that the temperature is at 25 degrees Celsius, which is 298 kelvins. So what we can do for each of these is simply plug our values of delta H for the first one, and that's in kilojoules, over our Kelvin temperature, 298 kelvins, and when you do that, you're going to get 7,450 joules per Kelvin. Now what you want to make sure is that you are paying attention to your units. In other words, I had kilojoules here, which would have given you an answer of 7.45 kilojoules per Kelvin, but then I converted that to joules. So if you did that with the second problem, again, you're going to have your 112 kilojoules over 298 Kelvin. You're going to get a delta S value of 0.376 kilojoules per Kelvin, which will give you 376 joules per Kelvin. And actually that's supposed to be negative, so you're going to have a negative answer there. You also want to remember, since you're taking negative delta H, our delta H value is already negative, so you're actually taking a negative of a negative, so your answer here is going to be positive. Here, you're taking a negative of a positive, so your answer is going to be negative. Okay, let's take a look at the next one. What we're doing here is we're calculating at what temperature this reaction is going to be spontaneous. So we're going to use delta G is equal to delta H minus T delta S. So to do this, what we're going to do is our reaction will be spontaneous if our value for delta G is negative. So if we set delta E equal to 0 and solve for our temperature, we'll get temperature is equal to delta H over delta S. So we're simply putting our values of delta H and delta S and then solving for the temperature at which the process will become spontaneous. And the trick to this is going to be knowing is the temperature going to be greater than or less than. So anyway, let's just do the first problem together. So we'll get temperature is equal to, now we want to make sure our units are consistent. Notice that delta H is in kilojoules and delta S is in joules. So what I'm going to do is put both of those in joules. So I've got negative 18,000 joules over negative 60 joules per K, and that's going to give me an answer of 300 kelvins. So the idea here is, alright, at 300 kelvins the process is going to be spontaneous, but is that temperature is greater than 300 kelvins or less than 300 kelvins? So what you could do is put that into your problem. In other words, think delta G is equal to negative 18,000 minus T delta S, and then think about when you get your answer there of 300 Kelvin, you want to think if you increase that to 301, so in other words, if you increased your temperature to 301, you have got a negative minus a negative. So what you're trying to do is make that value of delta G negative. So you've got a negative times a negative, which is going to be a positive. So what you can do is put in values for your negatives and, well, for your negatives. So in other words, what I would do is I would solve for delta G using negative 18,000, and then since you know the cutoff point is 300, put in 310 and then put in 290. One of them is going to give you a positive answer and one of them is going to give you a negative answer. 290 is going to give you a negative answer. So you know temperatures less than 300 degrees will make that process spontaneous. Now you can just think your way through it too, in other words looking at the negatives and positives, but if you're unsure, just put in hypothetical values. So for the next one, for letter B, if you do that, you're also going to get your temperature is equal to 300 K, but what you're going to find is that since delta S is positive, you're going to need numbers greater than 300 K to make that process spontaneous. For letter C, what you're going to have is delta H is unfavorable, in other words it's positive. Remember, a favorable delta H is negative, and your delta S value is also unfavorable at negative. A delta S value but that's favorable is positive. So when both delta H and delta S are unfavorable, that reaction will never be spontaneous. So you don't have to plug your numbers into the equation. On the other hand, if delta H is favorable, negative, and delta S is favorable, positive, delta G is always going to be negative. So again, you don't have to punch those numbers into the calculator. Okay, let's take a look at number 34. Number 34, you're predicting delta S of the process happening, and what you're looking at here are the states. In other words, you're looking at your two reactants, which you've got a mole of solid and a half a mole of gas, and you're creating 1 mole of solid. So your initial conditions of the system, you've got gas present, and then at the final conditions you've got solid present. So you've taken a condition where you've got gas molecules and turned it into a condition where all you have is solid. So you're clearly decreasing the entropy, making the sign for entropy negative. Now here you've got 1 mole of gas and 3 moles of gas, so you've got 4 moles of gas to start with, and then you turn that into 2 moles of gas. So again, you're decreasing the entropy of the system, making the sign for delta S negative. For this problem here, this is supposed to be an arrow here. What's wrong with my pen? You've got a solid turning into you've got 1 mole of solid turning into a mole of aqueous cations and a mole of aqueous anions. So again, clearly increasing the entropy of the system. The sign would be positive. And again, our arrow is supposed to be here. So you're going from a solid to liquid, again, increasing entropy. The sign for delta S would be positive. Alright, let's look at 36. In this problem, you're looking at which has a greater value of S, and again, it goes along the same lines. You've got dinitrogen monoxide at 0 kelvins or helium at 10 K. Again, greater temperature, greater entropy, so our helium has the greater entropy. Here we've got N2O gas at 1 atmosphere and 25 degrees Celsius. We've got helium gas at 1 atmosphere and 25 degrees Celsius. So when all things are equal, temperature, the state, and the pressure, what you're looking at is molar mass. So the larger molar mass is going to have more entropy, more opportunities for disorder, the more atoms and mass you have. Here we've got water solid at 0 degrees Celsius and liquid at 0 degrees Celsius. So again, temperature being the same, we're looking at state. So the liquid state is going to have more entropy than the solid state. Alright, let's take a look at number 40. You're calculating delta S for the aluminum bromide. Now for this problem, you're given some information in the book, so let me write that. For number 40, you're told that delta S naught is equal to negative 144 joules per Kelvin. So what that represents is that reaction taking place is going to have that entropy value at standard conditions. So what we can do here is set up our equation like we did with the delta H equations. In other words, we've got the value for the whole reaction. That's going to be equal to the summation of our products minus the summation of our reactants. Now in this problem we're solving for the product, so we don't know what that value is, so we're going to call that S, and what we're going to do is look up the entropy values for aluminum and bromine, and what we're going to find is that for aluminum it is 28, and for our bromine, what we're going to find is that it's 152. So then when we do the math here, what we're going to do is we're going to solve for x, and we'll get a value of x for 184 joules per K times moles. So again, we're treating this the same way we did when we were solving for delta H problems. We've got our value for the reaction, and it's equal to the summation of the products minus the summation of the reactants. Alright, let's take a look at number 46. Alright, for 46 you're calculating delta G, and again you're given some values here, so let me write those values down. Again, you're calculating delta G of the reaction. So told delta H of the reaction is negative 58.03, and then you're told delta S of the reaction is negative 176.6 joules per K, and again that's in kilojoules. So what we're trying to do is calculate delta G for the reaction. So what we're going to do is simply set up delta G is equal to delta H minus T delta S, and again we want to make sure our units are consistent here. So what we'll do is we'll keep things in kilojoules, so we'll have negative 58.03 kilojoules minus our temperature, standard conditions, 298 K, and then we've got 0.1766 kilojoules, or I'm sorry, kilojoules per K. And then when we do the math there, we'll end up with negative 5.4 kilojoules of energy. So then the next part of this question says at what temperature is this reaction going to be spontaneous. So again, what we'll do is rearrange our equation. T is equal to delta H over delta S. We're going to plug in delta H and delta S, and to save a little time I'll just write the answer. You're going to find that your temperature is 328.6 Kelvin, and any temperature below that will make the process spontaneous. And again, if you don't want to think through it in terms of signs, put some hypothetical data. Put in 338 and 318 and see which one gives you the spontaneous or the negative value for delta G, which would make it spontaneous. Okay. All right. For number 48? You have two processes, and which is thermodynamically more feasible. What I'm going to do is just talk about this one instead of going through all the math. What you're going to do here is you're going to calculate delta H of this reaction. Delta H of the reaction. You're going to take your products minus your reactants, and what you're going to do is look up your values for these formation values in the appendix. And then what you're going to do is calculate delta S of the reaction by doing the same thing. You're going to take the products minus the reactants, and what you're going to find is that for the first reaction, your delta H value is going to be negative 88 kilojoules, and your delta S value is going to be negative 247 joules per K. So what you can do then is plug those values into your delta G equation and then see if delta. So what you're going to do is calculate your delta H, calculate your delta S, plug into your delta G equation and solve for temperature. And what you're going to find is that you get 360 kelvins for that first reaction to happen. If you do the same thing with the second reaction, what you're going to find is that you're going to end up with a delta H value that is going to be positive, and you're going to find a delta S value that is going to be negative, so that second reaction will never happen. So the first reaction is more thermodynamically probable. In fact, it's the only one that will happen. Alright, let's take a look at number 50 real quick. Here you're given reactions, and what you're trying to do is calculate delta G for the overall reaction. and you're given delta G values for the combustion of C6H6, combustion of carbon, and combustion of hydrogen. So what you're going to notice is that this is the same type of problem that we solved with the enthalpies, where we used our formation data to solve the problem. So what we want to do is solve for the formation of C6H6, which would be that value. So we have the value for the whole reaction. In other words, you've got negative 63.99. That's going to be equal to the summation of our products. Now in here, what we're going to do, remember, we want 1 mole there, so we're going to divide that by 2, divide that by 2, divide that by 2, divide that by 2. So we're going to have 6 times negative 394, our value for carbon dioxide, plus 3 times our value for water, negative 237. We're going to subtract our reactant, which is going to be our X. And when we figure out our value there, we'll get an answer of 125 kilojoules. Now what you could also do with this problem is rearrange your reactions, cancel out what we need to cancel to get the final reaction, and then add up the 3 delta G values. Just make sure that you manipulate the delta G's the same way you would change those reactions. And to save a little bit of time, I'm going to not do that. Alright, so for the last one, number 54, what we're trying to do is determine, we're trying to calculate delta G for the reaction given delta G values for the POCl3 and for the PCl3. So that would be our delta G value for the POCl3. That'll be our delta G value for the PCl3. So what those are formation data. That's formation values also. So what we're going to do is simply solve delta G of the reaction by taking our products 2 times negative 270 minus our reactants 2 times negative 502. And what we're going to find is that we get a delta G value equal to 464 kilojoules. If we want to find if that process is spontaneous, again, our delta G value is positive, so it's not spontaneous. And if we wanted to calculate what temperature it would be spontaneous, we would put in our again, we would rearrange our delta G equation, so T is equal to delta H over delta S, and we are given the delta H values and delta S values from the problem. Yep. So then when we solve for temperature, we would get 2,890 kelvins. So clearly a high temperature to make that process spontaneous. Okay, that's it for this homework. This is a pretty long podcast, so if you've watched this and you have questions for class, we can maybe clear up a few things with these last couple of questions.